Hey everyone. Recently I found out about this cool company called Basetime. They work on making transformers run very fast for end usage, actual deployment for customers. And I thought I understood transformers pretty well. I mean, by this time I have hundreds of pages of notes from all the research papers I've read over the years. And yet, when I looked at some of the things that they were doing, I mean, it was like gobbledygook. I didn't understand most of the words they were using. So I spent the past week digging into some of these techniques they mentioned, and there's a lot of really interesting stuff here that I wanted to share about. This is going to be a little bit more advanced than most of my videos. You will need to know how the transformer architecture works by default, but with that out of the way, let's look at how to make transformers run real fast. The first thing to understand is that for transformers in inference, when we actually want to deploy them, there are two very different types of phases that they run in. The prefill stage is what we start with, it just happens once, and that's where we send all of the input prompt tokens into the model to be processed all at once. Now, in everyday usage, I'm sure you've sent very long pieces of text to LLMs, even files. There can be a lot of tokens here, and there is a lot of compute involved. Plus, we don't want to wait around very much, so ideally, this prefill stage, it has a very short time. It gets done very quickly so that we can start moving on to the stage we actually care more about as end users, which is decode. Decode is where a transformer will actually create output tokens for you. In a naive implementation, this will happen one token at a time. And obviously, if we're processing one token at a time, you can intuit that we're going to use a lot less compute. We'll explain why in a moment. But here, we actually run into another challenge, which is that we end up relying on a lot of memory bandwidth and memory storage. So we'll look into these two stages throughout, just, remember them as we explain why one relies more on compute, one relies more on memory bandwidth, to the point where we have actually techniques where we send one of these tasks to one GPU that has a lot of compute, another to a different GPU that specializes in having more bandwidth. That's called disaggregated serving. Anyways, when we think about this in more detail, more quantifiable terms, the way that we determine whether we need a lot of compute or bandwidth for any particular task, we can use something called the Roofline model. This helps us quantifiably determine for the specific hardware we're using and these specific functions that we're running, are we bound by compute? Will we get faster if we get a bigger GPU? Or are we bound by memory? We'll get faster if we, have better interconnect to move data around. The general theory is, if we have a GPU, let's say it can support 10 teraflops of compute, it has a theoretical maximum amount of computations it can do in terms of flops per second. But in order to reach that maximum of having compute-bound tasks like we'd expect in prefill, where we're doing a lot of math, well, we need to be able to get data to the GPU fast enough so that it's always busy. It's not just waiting around for the inputs to its functions. So we have to increase our memory bandwidth in gigabytes per second up until the point where we can be compute bound, and that is a good problem to have. Until we get to that point, we're going to be memory bound, where we're waiting around for data to be delivered. And until we get enough data, well, we can't maximally use all the GPU cores, so we have room still left on the table to improve. Now, what we want to look into is we can, empirically measure this. We can measure flops per second with the performance measurement units on the GPUs. We can measure bandwidth. in terms of actual reads and writes, also counted on the GPUs. But why do we think that decode tasks, they usually end up in the memory bound stage? The first thing that we need to look into to answer this question is just a brief reminder of how self-attention works, because the self-attention layers in transformers, they happen to be the key to this entire picture and what most of the compute, most of the memory, most of the optimizations are focused on. As a very quick reminder, with self-attention, you take some tokens. So in the case of our transformers, these are the output tokens that we've generated, for example. And we will do some matrix-matrix multiplications with some weights to get the query, key, and value matrices. So we just, do a matrix multiplication with X and get 3 new copies slightly modified by our different weights. For the actual attention computation, now that we have this data, we will multiply the query and the keys to figure out how similar they are to each other and run them through a softmax function to accentuate tiny differences. And then finally, we take these attention scores, which will be higher when the query and the key are more similar, and we will multiply the attention scores A with the value matrix. So you can see there's a fair number of matrix-matrix multiplications going on here to generate the query, key, and value matrices, to actually compute the attention scores, and then to compute the output again. Now, when we do all of these matrix-matrix multiplications, the reason that we tend to have memory issues, well, all of this grows in the order of n squared. That's because if we have, let's say, 5 query tokens and 5, key tokens versus 6 or 10, when we're doubling the input size, we're quadrupling the amount of work that we're doing. So if you take a look at the matrix-matrix multiplications, each of these positions involves a long dot product, and we end up with the n squared positions. So if we put in this case, 5 input tokens, then we'll end up with these attention scores that are 5 squared. So clearly we need a bunch of memory to store those n by n tokens. And for each of these positions in a matrix, you have a full dot product going on. So that's a lot of computation as well. So we can see that attention is very costly if we try to do it in a naive way. So the first category of optimizations in transformers is how do we deal with this problem? Because like these days we're certainly not sending in or getting out 5 tokens. We'll do thousands of tokens. Sometimes we'll upload a file to an LLM and we'll have hundreds of thousands of tokens. How can we manage this? The first fix to think about when it comes to the inference side is that the queries, these are the things that we want to figure out. Okay, I am currently in the process of outputting 1 token. Which other past tokens is this related to? If you think about that, unlike training, we don't have many tokens that we need to compute attention across all at once. So instead of having a full query matrix, we'll just have 1 vector for the current token that we're working on, which reduces from a matrix-matrix multiplication, which has, O of n squared outputs, to just a matrix vector multiplication, which has, n outputs for n embedding dimensions, n tokens, etc., etc. So that's one way that we can save a little bit of computation, and this is free. There's no downside here. But the next way is something called key value caching, and this does have some trade-offs involved, so let's move a little bit more carefully here. When it comes to the keys and values, I talked earlier about how we have to do these matrix-matrix multiplications to generate them. Recall, we just take the tokens that we have generated so far in the sequence, so let's call them x, and we will multiply them by our weight matrices, our parameters. But do notice that x, the tokens we've generated, in each decode step, we're doing one at a time in our naive world right now, it just changes by one token. You have whatever tokens you had, generate one more, add it on, generate one more, add it on, and so on. So the key and value matrices, if we just did that full matrix multiplication to generate them, we're repeating a lot of computations every time because, a good chunk of x has not changed since last time. If we recognize this, what we can do is we can start catching the old values that we had computed. So let's say, these values were computed from x1, the first token, these were computed from x2, the second, and so on and so forth. On the fifth iteration, only x5, that is the new token. So we only will compute the values needed for these, new token key and value pairs. All of the rest we can cache, store in memory, and just pull them in without doing any computations again. So this will allow us to drop, all of the tokens that we're computing. Instead of requiring n-squared calculations for the whole matrices, we can just do n calculations for the one position that we need to fill in for the new token. The obvious drawback to this is that, okay, now we have reduced the number of computations we need, but the memory usage, it goes up very, very high. In fact, I did a computation for GPT-3 using some parameters. The actual size of the model parameters, even with 173 billion parameters or so, it only takes up around 310 gigabytes. But when we look at all of the different self-attention layers, each having their own KV cache that is just growing and growing and growing as their output size grows, when the KV cache gets full, it's almost 15 times higher. It takes 15 times more storage to take all of these key and value pairs, store them so that we can avoid some computation. So this can be quite challenging. Even with modern GPUs, you maybe have 16 to 100 gigs of memory. If you're storing something like this for such an old model, imagine for the newer models that we have. So this is just not very sustainable. So now we have a new problem to target. We reduced the number of computations needed in inference, but now we have to figure out how do we get the memory cost down for the KV caches so that we can use this technique for larger and larger models. There are a few different things we can do here. The first thing that's kind of intuitive, okay, we have, the amount of storage growing by O of n squared. What if we just limit the size of n? What if we just, try and make models smaller? This is something we should always do. So we should always try to have pruning approaches where we take the weights that make the least difference. They have very small contributions to the activations in the model, and we'll just drop them out. And then we'll, update the model to work around this, then drop out some more and update more. We do this iteratively to figure out which activations and which weights actually matter the most, and we preserve those. This actually tends to have benefits for the hardware as well, where some hardware is especially good at skipping these sparse parameters, as we like to call them, so these zero weights. So we're not only saving on storage, but also we can make compute faster sometimes. There are also approaches like distillation, where we take our full model and get a smaller model set up that can mimic its outputs. So we can try and get almost the same quality, but at a smaller size. So again, reducing the size of n. There are some approaches like quantization, but they don't actually target, the KV cache size. They do reduce the parameter size, but as we saw, sometimes that does not make much difference at all. The last thing I'll say is that there are a lot of complicated approaches to change, this attention calculation itself, so that you don't have O of n squared calculations. You can reduce them to smaller growing variants. So you can look up sparse attention or efficient attention if you want to learn more there, but that might be out of the scope of this tiny overview. Now, even after we have addressed the memory costs of this KB caching, there is still one last hurdle, and it is actually a very, very important hurdle if we want to make transformers run reasonably fast. When we described the decode stage, we said that we would run the output one token at a time. So we have our full transformer, hundreds of millions of parameters, this KB caching, all of this computation, and we use all that for what? To generate like one word, like I, or, had. This seems very inefficient. It seems like it would be hard to scale up because no matter how we use smart strategies, and there are many, to distribute all of the computation across different GPUs, if we're still, bound by the amount of data we're pulling in from the caches, it's fundamentally not going to work well if we continue to generate tokens in sequence or serially. So how can we break the chain? How do we, avoid all the waiting from one to the next to the next? This is where I found a lot of interesting ideas. In fact, one of the main approaches here, Eagle, is actually from a prof at my university that I should probably reach out to. Anyways, the category of approaches is called speculative decoding. The basic premise is that you have some kind of draft model, which is going to be very small, and try and propose a full sequence of output tokens in one go. And then the big model, instead of going through all of the computations to generate one token, it'll just take the sequence of tokens generated and verify, are they good or are they not? So it can keep the ones that it thinks are good and then discard the one that it thinks isn't good. Before we get into the, minutiae of the approaches here, the key benefit of doing this is that when we have at least, one token that the big model will accept as this is good, then we can get benefits, we can get a speed up. The reason is that for each of the good tokens, while the big model is running, it didn't have to do multiple computations to get each of them, so it just gets them for free. And while it's doing the computation, it can still produce the one token that it usually would. So that part is always happening. So as long as at least one of these is being accepted, then the big model is getting free tokens for the same amount of work. Now, a few different ways to actually formulate this in a little bit more detail. There is an older architecture which is more simple. It's called the Medusa architecture. This is where you take all of the computation of the big model, and just before you get to the last decoder layer of the transformer, instead of doing, the conventional mapping so that you can go from that last decoder output to a single token, we'll actually train multiple heads, Medusa heads, which are just simple, let's say tiny neural nets in this case. They just do some linear mappings where each head will be responsible for generating a different token. So one head will generate, token 1, another will generate token 2, another will generate token 3. They just all use that same input and map to different tokens as outputs. Another alternative to this is the more modern Eagle architecture, where you don't have all of these separate heads with their separate parameters and weights. You just have one, auto-regressive decoder-like layer, where you take whatever parameters it has, and then on iteration 1, you take the output of the final decoder there of the full transformer, and then you run it through this tiny autoregressive layer. It will produce one token, and then the input for the model to be run again. So you generate the first token, get the output, feed it back in, generate the second token, get the output, feed it back in, and so on. So you can share the parameters. So these tiny draft models, they're not too complicated. The basic architecture seems to make sense. You take some input, whether, it's a fixed input or iterative inputs, and then you generate these multiple tokens. But then what about the big model? What about the full transformer? How do we get it to verify tokens instead of just generating a single token? This is the part that I found interesting. It is a little bit complicated, but not too bad. We'll work through it. So the way that the big model, the full transformer, is going to verify tokens is that when the small speculator model is running, it will still produce, this typical thing that a transformer output does. We will have all of the tokens that, are being produced. Let's say these 4 ones. And then we will have all of the probabilities for different words that could go in those tokens. So let's say we call these probabilities Qi for the draft model, right? Whenever it is finished with the creating its speculations for what the sequence of tokens should be, we'll have, let's say, 4 output tokens and then probabilities for all the words that it thinks could go there. The full transformer is also going to produce the same thing. As we run the transformer, all of those tokens that the speculator produced, they will be sent to the transformer as, inputs that are appended onto the existing sequence. So then the transformer runs, and it also will have probabilities for all the words that could go in those token positions when we get to the end of the transformer. So in verbal form, before we break down this complicated formula, the goal is that we will want to accept words from the speculators, have the big model verify them, approve them. When the big model, its probabilities, Pi, they're at least as high as the draft model's probabilities, Qi. If this is the case, then like the speculator is not doing any worse job. It's not introducing in words that are unlikely for the big model to say relative to itself. If that isn't the case, then we want there to be a chance that, the words are rejected, and instead we can just use the probabilities for words that the big model generated and use them to select a word that has, relatively high probability. How do we relate that to this math? Well, it's the ratio here. So Pi, again, big models probabilities, Qi is the small models. If these probabilities, Pi, are higher than Qi, that means that the model is more likely to recommend the word, the big model, than the small model. The ratio will be higher than 1. You take the minimum, which is just 1. So you always accept those words that are more likely or just as likely for the big model to say compared to the draft model. In contrast, if the ratio is lower, so Pi is less than Qi, the draft model came up with a suggestion, but the big model thinks, yeah, this doesn't really seem like a plausible generation. This ratio will be less than 1. So the probability that we choose it will be less than 1. We might accept it for a little bit of randomness, but more often than not, we might reject it. And so instead of taking the word that the draft model thinks is appropriate, in that case, if this was rejected, that token, we would just look at the PI, so the probabilities of words for that ith token for the big model, and just choose a word from there. Because of this, we have a quality guarantee. We have the output being statistically identical from speculation versus just running the big model alone. And that is the key part. That's really interesting because it allows us to have a mathematical guarantee of quality when using this technique, and we can just justify, okay, if we have enough acceptance rates, then we will in the end have a benefit to using this in terms of computation versus just the big model alone. So those were some of my main takeaways, some of the interesting techniques I found that Base 10 was using. Hopefully some of this is also interesting to you. And if you are curious to dig more into the topic, I would highly recommend that, especially with these speculators, there's a lot of ongoing work here. Eagle has like 3 variants now, so would highly recommend you read some papers there. And also KV cache, that's very big topic and very pervasive technique. So worth looking into all of the new concepts that have come out for how to optimize them that I still haven't heard of.